Okay. So I'll do a small introduction just for the crowd. And so welcome all for our series now, our mini lecture series on network and inference. Professor Timme is a very renowned figure in the field. Sorry for the niceness of the microphone, but I have to hold. So Professor Marc Timme is a professor in physics and math. He studied at Würzburg in Germany, then Stony Brook in the US, and then Göttingen in Germany. He's then moved to doing a postdoctoral research position at the Max Planck Institute for Flow Research, and then as a research scholar at Cornell University in Ithaca. He was then selected to head a broadly transdisciplinary Max Planck research group for network dynamics at the Max Planck Institute for Dynamics and Self-Organization. He also held a visiting professorship at TU Darmstadt, and he was visiting faculty at the ETH Zurich Risk Center in Switzerland. He's currently a strategic professor and the head of the chair of the network dynamics at the Cluster of Excellence Center for Advancing Electronics in Dresden and the Institute for Theoretical Physics. He was the co-chair of the Division of Socioeconomic Physics of the German Physical Society from 2014 to 2022. And since 2018, he has been an honorary member of Lakeside Labs in Austria. He has also acted as a national high-end foreign expert to China and as a mentor for female postdocs, which is initiated by the Leibniz Association in Germany. His research focuses on collective dynamics of complex systems. He develops first principle theory and integrates it in data-driven modeling to establish generic fundamental insights that drive applications of complex dynamical systems, including bio-inspired information processing, energy system, collective mobility and transport, as well as systemic sustainability. My knowledge of his work goes back to when I was a master's student, and I based my work on, my master's thesis was based on his work on inference. It was a Kuramoto model, and so it's been an inspiring figure in the field, and I hope you're going to get the best out of it. He's staying with us on many occasions, so it's going to be today, tomorrow, and the week after on two kind of distant lectures. So I'll leave the ground for you, Professor Timme.
Yeah, thank you very much for having me, and welcome all of you to the what you call lecture series. There are 4 lectures total, like 4 events. The slides are prepared. The number of slides per lecture, per event, are in very different numbers. So it might be that I go over, like I spend more time in one lecture than in the other one. I might also skip some of the stuff. Today, I'll basically introduce some of what we do in general, a bit background on nonlinear dynamics, like an introductory session, and then I share one example of what I find an interesting phenomenon in the dynamics of networks, which has something to do with the substructure of networks. Okay, so you all see my screen, and some of you will know the picture, some won't. This is there's one distinguished pixel here, which is bluish, and this is our home. All of human history has happened on that tiny pixel. Quoted from Carl Sagan, who was involved in planning the trip of Voyager 1. A spacecraft which was launched in 1977. The image was taken in 1990, and so there was a special command that Voyager 1 turns back, flying out of the solar system, turns back and takes an image of, I think, all or most of the planets at the time. It still communicates with Earth today, despite being launched very long ago. And it passes through interstellar space, so outside our central solar system, since 2012, and it will do so for the next 30,000 years when it will reach the next solar system. So this naturally poses the question of how far can we reach, we as humankind, what is our scope? And one of the challenges Voyager has, it runs out of energy in 2025. So this is a very similar situation than we have on planet Earth. We run out of carbon budget within the next couple of years. I just today shared a tweet. By the way, if you want to follow me, it's Marc Timme on Twitter. Shared a tweet on how many years we as Germans could contribute emitting carbon dioxide, given our average German budget. And if we want to keep climate change within 1.5 degrees Celsius, the total number of years is something like 4, maybe 5. So it's very low compared to what we think. Okay, we can continue a couple of years and maybe 2050 we should become carbon neutral. It is not like that. And if you take care of Germany's past emissions already, Germany should have stopped emitting anything like zero carbon emission many years ago. So how far can we reach? That's also a motivation of what we as a research team do and our areas of application. And I'll talk about that very briefly in a few minutes and give one example of how we approach this with our physics and math background. So zooming in, we are about here. You will be, can't easily see that, but I think you will be about here. Is that right? Tell me.
A bit below.
A bit below here?
Yes.
Okay, I'm not so knowledgeable. I just know it's somewhere here, and I know roughly where Israel is, so it must be north of it. So nice. Yeah, and I would have liked to come, but currently my time schedule doesn't accommodate that. So there are a number of 21st century challenges, and climate change is only one of them. There are economic instabilities for those who lived through the 2008, consciously lived through the 2008 financial crisis. There's the next one, maybe coming up, given at least in the US and the directly connected countries, because they raise their interest. They have risen their interest rate, I think, 7-fold now within a year or so, and that's more drastic than everything that has happened ever. There's obvious environmental damage. Classic examples include some great lakes which have dried out in Asia. There's also massive loss in biodiversity. So if we continue like that, we will probably lose 90% of all species within the next, I think, 100 years or so. Of course, it's hard to estimate, but the sheer quantity is dramatic because, as all of you know, everything is networked. So once we lose certain critical species, we lose also humankind as we know it. For example, if a small subset of insects, including bees, can't pollinate certain plants, we will essentially run out of food very, very quickly. We are talking 2 years. So once that collapses, and no one knows when it does, we have a big problem. That's one reason to invest in preserving biodiversity. Then we have all experienced COVID-19 and also other previous pandemics. There's epidemic spreading. It's on the molecular level. It's a problem, but there's also epidemic spreading of malicious ideas. for example, that one country can just invade another country, or that we could just remove democratic structures and instead have one subset of people dominate another one by whatever, by money, for example, or by force. And there's, of course, massive resource and energy limitations. There's currently, we are struggling and working on it. I mean, many companies and cities and countries are working on removing or lowering the impact on resource limitations. For example, rare earths is a problem. We all of us want to have electric vehicles in 10 or 20 years. And if you don't take care of what goes into the batteries, for example, and into the production of these vehicles, you have a big problem. That's similarly true for existing internal combustion engine vehicles, but it's just one major issue to discuss. And that is true for essentially all elements, including water in particular, including very basic seeming things like sand to build buildings. We need sand, but there's only certain grain types which are appropriate for building. And most of that is from rivers and beaches. So it's not that you can go to some big desert and fetch a lot of sand and use that, because the grain form is not appropriate. So, and one aspect I'll touch on today very briefly, and we have a big subgroup on working on that, is systemic solutions to transport and mobility. Like, how can complex system science contribute to understand current and possible future transport systems and make them more sustainable? And overall, all of these systems are interacting, large collections of interacting agents with some unknown structure or parts of the structure, with sometimes unknown players, for example, biodiversity. We don't even know all the species, but we know that we lose a lot every year, essentially every day. So that's just as a background motivation, and that's also my motivation or one of the big motivations of pursuing research onto the dynamics of complex systems and networks. And in my talk, I'll focus on multidimensional time series, like what happens if you record the dynamics from many different variables in a system at the same time. The focus will be on network inference, and in my fourth lecture, I will also briefly present newest results on non-equilibrium tipping. The question is, can you predict when a system which is driven from the outside, at which driving amplitude the system loses its original state and goes to another state which might be undesired? For power grids, for example, which is also a big topic we are working on, that is to mean that we go from a normal operating state to some state which is not normal operating, meaning it includes blackouts or unreliable power supply. As mentioned in the introduction, thank you very much for the kind introduction, Sarah. I'm at TU Dresden. I'm teaching in the Institute for Theoretical Physics and have some other activities there as well. My main part of the group is sitting in the Center for Advancing Electronics Dresden, which has been an excellent center. It's not anymore, unfortunately. I'm a member of the Cluster of Excellence Physics of Life, which is a biophysics cluster trying to understand self-organizing phenomena and develop technologies for living matter. And I'm associated with Lakeside Labs Klagenfurt, where I try to exchange our theoretical mathematical ideas about self-organizing network systems with engineers and computer scientists who actually do something with it or build stuff, which we typically don't. We just do some examples. yeah, the work today and also in all the other lectures is strongly supported by a number of former or existing PhD students and postdocs. And I'd like to mention here already Malte Schröder, who is leading our subgroup on collective dynamics and sustainable mobility. Jose Casadiego, who has been involved in most, which I present on network inference, and he has been a PhD student and then postdoc with us. And Moritz Timme, who is a finishing PhD, worked on the non-equilibrium tipping. I have 2 years ago, I've transitioned to calling the topics I'm interested in 4D complex systems. And I don't mean literally 4 dimensions, but I mean that there are 4 Ds involved. One is that they are always, I'd start from the last one, they are always dynamic. They are typically discrete, so they're entities which interact with each other and they are somehow defined. They are distributed, so it's not that the mean field solution is nothing we are working on, but typically we try to go beyond any mean field approaches and ask for what does the spatial or otherwise distributed nature of these systems, how does it influence the system dynamics? And very often these systems are driven. So that it's not that you have, if you describe them, for example, by differential equation, ordinary differential equations, they are typically not autonomous, but they're non-autonomous. And driving can mean something very simple, like, for example, kicking it once and then relaxing back to a state, not touching the system otherwise, or moving a parameter and keeping the parameter at a new position. Or it can be something very complicated, which is you drive every node of a power grid by consumer and feed-in properties in stochastic, unpredictable ways. Like, how does the system react? So that's the full range of topics we address. And all of our work is based on mathematical and theoretical foundations. And I've listed a few topics here: information routing, for example, distributed processing of information, or even channeling of flows, disorder scaling and stochastics, inverse problems, which is the opposite of this traditional approach, going from structure to dynamics, going from dynamics back to structure. Can you say something about structure if you know properties of the dynamics? On nonlinear fluctuation responses. Then there are 2 application areas where we direct our research to, or substantial part of the research. The first is on sustainable energy and mobility systems, and the second is on biological and bio-inspired systems. I already mentioned renewable energy systems, power grids, and networked public mobility. So we are more interested in public mobility, in the sense of publicly available mobility. It doesn't mean that the public funds that. It's not only buses, it might also be taxis or bike infrastructure or bikes, but it's available to everyone. It's not that we are interested in how a certain car works or something. And it's always collective in the sense that, so complex systems is always the entire thing, the entire system which we are interested in. One small study we are currently performing is trying to estimate when electric vehicles have taken over, basically. And that's the surprising thing, it's much faster than you might think. We currently, worldwide, we are below 10%, and it will take less than a decade to get above 80%. Last topic is has shrunk a bit recently because the postdoc left, and there are still 2 or 3 people working on that. And neuromorphic computing, like how can you use ideas from biology to process information? How can you control networks, and how can you reconfigure or build devices in ways which are robust, sustainable, and so on. The picture on the right here, we can circle that, is a robot which takes a walk, an autonomous robot. It has, I think, of the order of 20 sensors and also of the order of 18 motors. In principle, all working independently, and our 2010 paper for that was about trying to understand how a small neural circuit with simple means can control such a complex object. And the controller itself, I mean, there was distribution of signals, of course, but the control unit itself was just 2 formal neurons, like 2 units, like something like that. It was feedback loop, and then you have signals coming in here and the walk signal going out there. And it could realize more than 10 different types of behavior, like walking in different gates, walking up slope, down slope, lying down, turning around, walking towards light, running away from enemies and so on. And this slide is just to give you a broad scope overview of what we do, and I won't go into any more details. So if you have questions, just ask after one of the talks. I'm also happy to discuss any of the topics in a later lecture, either during these 4 lectures or in another one, in more detail, but then I would need to focus on that and not on the network inverse problem, which I'm currently wanting to do at least starting from tomorrow on. So take home from this, it's always dynamic. Like I can't imagine we do something which is like structural only. If we do that with a structural only, we always are motivated by the dynamical question. It's discrete units, they're distributed, and very often they are driven. And the most important word here is systems. So we are never interested in individual units, essentially never. So it might be that the systems are very small, like this one, 2 units, which have a collective effect. By the way, for the robot controller, we used chaos and chaos stabilization, controlling chaos to get different kinds of motion, different kinds of signals out here. Because chaos has embedded in itself many different unstable periodic orbits who can exploit all of them. And the state of the art until then, until 2010, was you need a specific controller for each type of walking pattern, each type of gate. So it's always about systems, and well, they're complex and you understand what that is. If you have any question, either technical question, or you didn't understand some detail on a slide, or you want to ask some broader question of what we are interested in and how we would approach that, please feel free to ask during the lecture. There's also time after the lecture. I will leave time for asking questions, and I'd rather cut out material from the talk. So please just show up, and you probably have to shout so I hear it, or raise hand in the room, and someone has to tell me that you actually do, because I'm looking here when I read the slides and look into your camera, whereas I see you only there, so it's hard for me to simultaneously see. Yeah, so topic of the 3.5 lectures will be inverse problems, getting from dynamics to structure. The last lecture will be about the forward direction, going from known driving signals to predict fluctuation responses in nonlinear systems. And although nonlinear dynamics is like half a century old at least, even conservatively speaking, we have unraveled a challenge which apparently no one has seen, and that's because we are all educated like in standard, basic, simple models, or in physics, as applied math on physics, and all of the textbook examples have a certain symmetry, or property that avoids us seeing the phenomenon. And I go to that. There's an interesting nonlinearity in the responses. And today I'll mention very briefly, just as one example, one aspect about networked public mobility. And that's what I do now. So there are many challenges in future mobility and also in current mobility, as you see. That's one of my favorite pictures, because it shows one, a network, and B, a collective, and C, that the problem is everywhere. Like it's a distributed problem. You have congestion, and you can't say where congestion starts or ends. It's just everywhere it's congested. My best personal example of that was trying to drive into San Francisco in, I think, Friday afternoon, and it was looking similarly. It was really horrible. Just the streets were a bit wider. Currently, there's a discussion in Germany whether we should extend highways and put new lanes. And it's known scientifically that if you do that, you wait a decade and then you have more congestion. So, but it's not only congestion which is the problem. Congestion has problems with, or comes with problems of stress and health non-benefits. It has this is a map of Germany with particulate emissions. Some regions are particularly strongly affected, like here and there. And one problem with cars is that even if you have fully electric or renewable cars without any combustion, half of the particulate emission comes from wheels and all kinds of other stuff, basically wheels. So just replacing cars, like combustion engine cars, by electric cars will not make 100% sense, right? You have to, in addition, do other things. Yeah, so this is stress level. 2/3 of German motorists feel stressed. I'm one of them. If I'm traveling by car, which I rarely do, but if I do, typically longer distance, it's somehow stressful. So there are many, many challenges of future mobility, and these, I argue, are complex systems challenges. What is at stake? I mentioned already congestion, health and accidents, time and well-being, our environment, energy waste, infrastructure, economies like businesses and entire countries. And it will get worse because population will get denser and larger, and the cities will grow, so you even get more compacted stuff. And then there are technologies which promise, okay, in the future, we will have solutions to it. In the future, mobility will be simultaneously more shared, more flexible, more ad hoc, more electric, more autonomous, more cost-conscious, more intermodal, and therefore seamless, interacting cars and therefore networked, and it will operate at larger volume density, number of users, and number of modes. I don't know what's going on in your country, but in Germany, you have these scooters everywhere now. Like every city, every bigger city has scooters, and they're parked on pedestrian sidewalks. They're sometimes parked on roads. I've seen one in a tree, up in a tree. And well, more modes are not always a good solution. I'm not saying that scooters are bad. I just say that the entire problem is very complex. Why is mobility a complex systems and a data analytics problem? First, it is basically always the question of what a network collectively does, like how is the network dynamics, because you have many entities and there are interactions among them. Second, it's an understand, predict, and then control problem. If you just apply standard control theory, for example, because of the network nature, you will lose a lot and get phenomena which you haven't predicted. One example is Breast paradox, if you know that. I'm happy to tell you at some point. Breast paradox is meaning that if you add a new street to a street network, for example, or any flow line to a flow network, you would assume that traffic gets easier or flow gets easier, but that's not always the case. It depends where exactly you put it and the conditions. And third, the phenomena known from complex systems, in particular physics, are also present in many transportation systems. For example, hysteresis, bifurcations, phase transitions, symmetry breaking. And essentially everything you learned in statistical physics or you learn as collective phenomena anywhere in complex systems science, you will find in one or the other mobility system. So what we need for major insights is good data. Good can be a lot, but it also typically means, for example, clean and appropriate. Appropriate is probably the most important aspect of the data. It doesn't help if you have a lot of data and they are not really informing conceptually thinking people. And that my past experience, like after my PhD, was with neuroscience questions, and some of the data the experimentalists recorded were very helpful for their own question, but then the more overarching question they were asking to the conceptually working mathematicians, computer scientists, and physicists, they could not address, although they had like stacks of data in massive resolution, everything, because they were just not appropriate. So we need good theory, and good theory can mean a lot. I could give a full talk just about that. In particular, it means that the theory gives you results which are not dependent on too many details of your setting. Of course, every model is a simplification of the real world. My colleague in Göttingen used to say that the best model of a cat is a cat, preferably the same cat. But of course, if you have a cat as a model of a cat, then you can't understand much about the cat because you just copied it. Yeah, and good modeling means also asking the right question, finding the correct, appropriate observables and order parameters, for example. And in our team, we strive for two conceptual cycles. One is the data and generalization cycle. So we start with a system which gives us some data. Then we try to explain, to first characterize the phenomenon, try to simplify the system which still shows the same phenomenon, understand that simple system, then generalize once it's understood, and then go back to a system, like approach it with, for example, numerical simulations or real-world observations. Ask from your simple theoretical model, like what can you understand? How can you possibly measure stuff? The second is that what I already mentioned is understand, predict, control cycle, go to systems. And it's not sufficient. Traditional method to just control stuff is not sufficient once you have a complex system. So I think I mentioned that already. So we always first go understand, then potentially predict and control. So part 0, collective inefficiency in ride-hailing systems. We have now taken data, which are 10 to the 8 approximately taxi rides in New York City, Manhattan. We have origins, destinations of taxi fields, and the times. We also have street topology, street network topologies with some 4,000 nodes and 9,000 edges. So if you ask how many paths you can go from any node A to any other node B, it's about 10 to the 8 path options. Of course, well, shortest or close to shortest path options. That's just the number of ways you can go. And this is what is recorded from a simulation. Okay, we now take those data and run a simulation on the Manhattan street network. And you see two curves here. One is the request rate. The gray curve is the request rate, and you see it varies over the course of the day. It goes up, sometimes it goes down. Well, at night, it typically goes down, like this is midnight, this is 12 a.m., 12 noon, and here around maybe 3 or so, it's minimal. It's minimal. And that's not surprising at all, right? And then you can ask in a given, you put a number of taxis, you will put 6,000 taxis in our simulation system to be able to cover most of the day. What you see is, of course, here, all the taxis are available, but at some point, for example, here, the number of the request rate rises, and simultaneously, the number of available taxis drops. The problem is, once the request rate drops again, the number of available taxis does not go up again, right? Instead, it goes down. It actually goes down to 0 and stays there for a very, very long time until request rates have come down to about half their maximum level. So here it's about 400 requests per minute, and here we have about 200. Okay, so this is somehow a gap, and this entire time the number of available taxis is 0, meaning that you ask for a taxi and the operator tells you there's no taxi available, please wait a bit. And so this is what as physicists, what you're used to, or mathematicians and computer scientists as well, draw a state space model. And a very basic state space model is just plotting the two variables against each other instead of against time. So here's the same data, the number of available taxis as a function of request rate, and you see that towards evening it drops to 0, it stays, and then goes up. And what you also see, there's this loop, which is the hysteresis loop, okay? So yes, hysteresis, which is expressing a kind of inefficiency in the system. So just if you are just below the maximum load, if you are here, you are completely fine, because if you then reduce the rate, you will just go up again. If your blue curve goes up, it goes this way up. Whereas after you are locked to 0, you go this way. So you stay at, you cannot make more taxis available. And yeah. So substantial system capabilities are wasted, and the system is inherently inefficient on the just because of the collective dynamics it shows. And if inefficiency is up to 50%, as you can see here, right? You can serve, I mean, all the requests here are served, but you have to drop request rates by a factor of 2 to get up again with the number of available taxis, meaning that the service quality becomes good again. So why and how does hysteresis occur? And so now comes this simplification step. So we do a very, very simple model. And first we ask what is going on in a very basic network. This is a network of 5 nodes, just for illustration. And the next thing I'll show you is a network of 2 nodes, okay? And you might think, well, why can you possibly understand that on 2 nodes? And I'll show you. Okay, so this is time axis. And at some point, a potential passenger wants to drive, okay, wants to take a taxi. Then it takes a while until the taxi is assigned. Say this is very small. Then there's a time until the taxi goes to the passenger. Then the passenger boards the taxi, and then it's driving to the passenger's destination. So there's a pickup and drop-off event and a taxi assignment event. Now, if the queue is empty, in other words, if out of the 6,000 taxis, say 90%, 10% are still available, like 600 taxis are available, and you would distribute 600 taxis across Manhattan, you can imagine that near every request, there is some taxi. Like probably takes 2 minutes or so, but roughly it takes not much time until the taxi is at your location, because there's so many taxis around you. So in a basic model, the taxi is at your location. So you ask at a certain house number and the taxi is just appearing. So that's the approximation we do. That's the time to pick up is 0, okay? And of course, it's not really strictly true, but it's small compared to the delivery. So if you go half through Manhattan, it takes, in the average trip length, actually in the data is about 20 or 22 minutes or so. And compared to that, the average pickup in an empty queue situation, so lots of taxis available, is really small. Like it's less than 10% of the time. So the total busy time of a taxi per request is just given by the drop-off time. Like this, you assign the taxi and the taxi comes there immediately. You are dropped off, and the drop-off time is essentially the time of the service. This means that the taxi becomes available quickly again. So if you have lots of taxis available, then the taxi which serves the passenger becomes quickly available again. That is a positive feedback loop. If you're good, if the system is in good state, it becomes quickly, it stays good. So the taxi becomes available again. If you have a congested queue and there's no taxi available, the next taxi, so assume there's no taxi available currently, you are asking for a taxi somewhere in Manhattan. And the operator says, no, we don't have a taxi, but the next taxi is yours. You think, great. But where's the next taxi? The next taxi, if you are in Lower Manhattan, is in Upper Manhattan. So it takes something like 15, 20 minutes to go to your place. It actually takes the average time it takes for a trip to go by taxi for the empty taxi to just come to your position. So there's a pickup time, which is typically approximated by the typical time it takes to drive between any two places in the city. And then there's a drop-off time. And the sum of these two is the busy time of the taxi. So in the worst case, this is just, so distance is velocity times time. So time is distance over velocity. And so if you average that, you have the average time is, well, assuming velocity is constant, otherwise you get nonlinear modifications. But the average time here could be given by a multiple of the average distance driven in the city twice. So it's just, this is just 2 times the average distance, L for length, divided by the typical characteristic velocity, okay? So here, if the system is in a bad state, which you don't want, congested, it takes twice as long for the taxi to serve one customer than it does in the other state. So the taxi becomes available slowly again. This factor of 2 is also what you see here. The factor of 2, you have seen here, you have to reduce the number of requests per minute by roughly a factor of 2 to get your taxis available again. And the reason is precisely that. The reason is because if it's empty, the queue, if the queue is congested, you can't make it empty unless you drop below this request rate. So there's 50% efficiency lost because the same taxi could serve, if the same taxi is operating in an empty queue situation or not congested queue, it could serve 2 passengers in the same time it does with 1 passenger in the congested one. Now here we take a 2-node grid and we ask the following. How does it look like in a 2-node grid? So there are very basic requests that there are taxis driving and you either go from A to B or you can go from B to A, and it takes a while. There's a certain fixed velocity, and this is the history, this curve you get, okay? These ones are finite size effects, so don't worry about some small details here. And the inefficiency is like this, like how many transporters you actually need. Now, instead of assigning a taxi as you would think is fair, so first come, first serve is fair, you could say, okay, let's assign it in an unfair way. So in other words, if no taxi is available, you're calling, I want a taxi. The operator tells you, no, wait a minute, you might be queued later. We wait for more people to ask for taxis. And you would find it a bit unfair maybe. But doing that with a fraction of taxis, like 20%, 40%, 80%, you see that the hysteresis is reduced. So the larger fraction of taxis is routed unfairly by this definition of unfair. The less large does the hysteresis get. So in other words, we have to essentially go to 1. It's not plotted here because you have to route all of the taxis in an unfair way to get the system efficient. So there's a trade-off between fairness in this sense and efficiency. And so either you can choose whether you want to treat the individuals fairly, at least what some people think is fair, or you want to transport them quickly. And it's a challenge to actually tell people, look, we do it in this other way, which you might think is not fair, but it's actually better for everyone. So it's also a game theoretic question. And the phenomenon is not bounded by taxis or Manhattan or whatever. It's just a phenomenon which is due to queuing. So it's a queuing phenomenon, and it equally occurs in ride-sharing systems and so on. Yeah. So I said that, so multi-passenger and ride-sharing, whatever you want, it doesn't depend on the traffic network, on the request pattern, on any of the parameters. You can change, of course, absolute quantities here, but this is the reason, because it's so robust, this is the reason we can explain it with a two-node, very basic homogeneous system. And this illustrates that there are mathematical difficulties for theory if you have given a phenomenon. The phenomenon might be from a modeling standpoint, like a simulation, or it might be from a lab experiment, it might be from a field experiment, or just from data simulated, as we've just studied in the recent example. And these difficulties include a nonlinearity of the system. The system somehow has nonlinearities. It's typically high dimensional. If you have networks that have complicated connectivity, there are delays in the system, there are heterogeneities in the system, meaning randomness in space or among parameters, and there's stochasticity in the system, meaning randomness in time, basically. And a typical approach to resolve that, you have so many difficulties, is ignore them. Okay, as a mathematical modeling person, you can say, well, just look, we have this real network. This is of course a sketch, but a schematic network. Let's assume it's the average weight of coupling is like this, and so the total is that, and so my average influence of one node on the other is like this. So you can create a mean field model which looks like this. So everything is homogeneous, and then you can hope for being able to solve that analytically, make some mechanistic statements. The second is, which I've myself learned in the neuroscience community, is some local averaging. Like you say, okay, in a brain network, for example, you have some location, but no location is somehow distinguished against others. So here is a translation invariant, locally averaged network. And you might think that either this or that should be okay model for the entire system. And I will show you by example next that can be very bad, in the sense that specific links or even specific realizations of networks, like even if you draw two networks which are large from the same ensemble statistically, but they're slightly different, you might run into problems. And we will see that today, that two realizations make a big difference. And we'll see, I guess tomorrow, that individual links, no matter how large your network is, individual links can make a huge difference on the collective dynamics. That's the wrong blah, sorry. So part one, so the essence. By the way, how much time do I have today? Can you tell me?
It's up to you now. It's up to you how you plan it now from here on.
All right, good. So when will you sleep? You let me know if you're tired. What I do with my students, I have them get up to activate their brains. Maybe I do that after a couple of minutes. Okay.
Okay.
Okay. So first, I will. So today I have two more sections planned, and if it doesn't fit time-wise, I can also move some to tomorrow. First, it's about nonlinear dynamics, and then second is about network dynamics. The nonlinear dynamics is basically definitions and just some intuition, or for most of you, it might be repetition. I just want that everyone is on the same footing afterwards. What defines a dynamical system? You probably have seen models of dynamical systems in all kinds of ways. There are agent-based models, and differential equations, and discrete time maps, and whatever, stochastic processes, and all kinds of this. And I just want to put you on the same footing of what this means. So this now gets a tiny bit mathematical, and I have written it so it can be read by mathematicians as well, but it's really not difficult. So the first thing you have to do, and really the first, people forget about it, is define your state space. First thing, define your state space. You have states, small x, in some state space x. And what is actually the state space and what are your states is important for later analysis. If you do that wrong, you can run into trouble or just not be able to analyze your system. And a typical setting is, okay, you have either real or complex n-dimensional spaces, like vector spaces. You could have intervals or high-dimensional intervals. You could have a discrete finite number. You could also have a countable set like n or z, like the integers or the natural numbers. You could have spins, like this is like two-state models. You have, for those of you familiar with physics, you can have spin models where spin up and spin down are only two choices. I myself have worked with a so-called Q-state Potts model, which is like a small finite number of states here. And of course, there are any other choices, but you have to define your state space and your state. And it's not trivial. Sometimes, for complex systems, sometimes it might be easier to make your state space more complicated in order to be able to analyze them in a simple way. Actually, my very first paper was like that. You make a very, very complicated state space, which then has in that state space very simple dynamics. It was about rearranging aggregates. So you have a collection of particles, and they have some structure. Actually, they were on a grid, but fine. They have some structure, and now at a low rate, something happened. Like they may detach here. This one detaches and diffuses around and touches somewhere else. And you can imagine that if you have lots of these structures, then you get very, very complicated looking aggregates. They look like fractal structures. And the state space, if you define your state space as, okay, what's the spatial organization, which of the grid cells here, if it's on a grid, is occupied and which is not, your state space is looking simple because it's like two coordinates. And then many times two, like if you have n particles with two coordinates, you have n times two coordinates. So you have two n variables. But that's a very complicated thing to analyze. And this is what typically people did before. There were some exceptions. And what we did is change the state space, make one aggregate, the entire aggregate, one point in your state space, like the space of all aggregates. And one aggregate is just a point, and it has certain properties. Okay, then of course there's a time domain or parameter domain sometimes. And times are typically discrete or continuous. There's typically only one. Sometimes there's complex time, but I won't go into detail. Then there's the important thing is the rule of time evolution. Like if you have, it's of course linked to choice of state space. If you have a state space in a time domain, you need a rule of what your dynamics is. And there are different kinds of rules, and some of them are known to everyone, and some are less commonly known. Time continuous evolution rules are typically ordinary differential equations, or of course also if you have continuous continuous state space, it might be a continuous set of it might be partial differential equation, but also I don't talk about that. It might be discrete time maps, iterated maps, where the time evolution rule looks like this. The state at some next time step is given by a function, typically nonlinear, of the original state. And then there's a third class, which is known in mathematics as hybrid systems. I'll call that on the next slide. And then there are stochastic time evolutions, which might be all of these types. And there are myriads of definitions of that, like how you can describe it by large word description, for example, or in most general, it's just a stochastic process as a mathematical definition, or you can just immediately start with describing the entire thing by distributions of realizations of system states. And here I would like to briefly go into hybrid systems because I need it once in a later lecture. Hybrid systems are, as I said, discrete and continuous. And for instance, the ordinary differential equation time evolution is interrupted by discrete time events. For example, if the state time evolution crosses some subset. So if you have your state space, you have X here, okay? This is your state space. I hope I don't draw where there's supposed to be text. You have X of t. You evolve, and at some point there's a set S, which is a subset of my state space. Typically it's lower dimensional, like a plane or something. And once it crosses it, something happens. For example, it could just reflect from there. Okay, could just go here. So in other words, there's a continuous time evolution. This part until here, until the subset is a continuous time evolution. So that's an ordinary differential equation describing evolution here, ordinary differential equation here, and some extra rule, what happens when the system crosses this subset. And you might think it's not common, but it's actually very common everywhere. You think about it, like if we think of simple mathematical models of time evolution of systems of the real world, you typically do that. You have some separation of timescales or other features in like boundaries or constraints, which more or less force you to build hybrid systems. And a very basic example is you take a tennis ball and you throw it at a wall. And there are various ways of modeling that. The naive model is, okay, this is just Newton's law, because once you lose the ball, you don't touch it with your hand anymore. There might be some friction, okay, but otherwise it's just Hamilton's equations of motion, or Newton's equation of motion, all the time. But it's not true, because if there's a wall, then what you intuitively think is that the ball turns its direction around, just flies away from the ball towards you again. And only in second thought you might think, okay, what's actually going on? The ball is deforming itself. There's friction involved. It's some wobbly motion, then removes from the wall. But if that event is small, like short in time, you might be much better off in describing the system. But the hybrid system, time evolves with an ordinary differential equation here, ODE here, ODE here, and some discrete map here. Okay, so it's important that you understand that roughly. So please raise your hand or ask a question. If not, so you go towards that, and where x equals 0, so here is 0, you have the following. You have an interruption of the ordinary differential equation, which is just Newton's law. And then you have the change in velocity. Change in velocity at the wall. And that's modeled to be instantaneous. So you have the new, like immediately after the time t star, when it hits, it has a new velocity, which is sign reversed. So it goes away from the wall instead of towards it. And it has some energy lost. So there's some fraction of energy lost, meaning that you also lose some velocity. And then it's continuous time evolution again. The same happens, of course, if it were to hit here, right? If you hit the ground, it would also be some map, which is more complicated. Yeah, well, it's maybe the same type of complication. So the baseline here is even very simple looking systems are already hybrid systems, and hybrid systems, next message, are very different from what we know in ordinary differential equations. They naturally arise in all kinds of event-based dynamics, in particular in agent-based models. So if you have agents which have some internal state and they make some decisions or some action, they move somewhere, stop, anything like that, any event potentially makes it a hybrid system, which then in turn makes the collective features much more rich. In mobility models, agents may be drivers, pedestrians, vehicles, service providers. It might also be infrastructure, like, for example, a charging station or a parking lot. And these have, as I mentioned, novel and different collective phenomena compared to ODEs. They may complicate, or sometimes they may simplify mathematical analysis. For example, if you take the hybrid picture for the tennis ball, it's much simpler than analyzing the deformation of the ball. And it changes the numerical simulation because you have these events which interrupt any other kinds of dynamics. And we ourselves, I and members of my group, and even my former supervisor, so really since my PhD, have worked on hybrid systems. And one thing we found are unstable attractors. Unstable attractors are attracting sets which are simultaneously unstable. Typically, attracting sets are thought as stable sets, but they are not necessarily, and that's caused by a hybrid nature of our systems. We have revealed topological speed limits to network synchronization. So if you, and that was in a model for neurons, coupled neurons. So the idea is that if you increase the coupling strength, then the relaxation is somehow faster. Think of planets or something in a solar system. If you increase the gravitational constant, then everything gets faster. And if you increase it more and more, then the rapidness becomes essentially infinite. Okay, there's some relativistic limit, but before that, it becomes arbitrarily fast. And in our system, it wasn't like that. And this is the combination of the hybrid nature of discrete events and the non-trivial topology of the network. So if you're interested, I can always recommend this as one of my favorite papers ever. My favorite own papers. I like some of the other papers better, not mine. But and also what we found is overtaking among identical oscillators. So imagine you have phase oscillators, like one variable which just cycle on a circle. They are all the same. They're globally coupled, homogeneous coupling. Everything is the same. All parameters are identical. And they overtake each other. In a continuous time system, this can't work because you would cross an invariant manifold. And once you enter the manifold, you actually stay there. So it can't cross it. And this one, it looks like it crosses, but it's just a different mathematical structure. So here, what you see is that the early units switch order with the late units. So the blue-green one, first here, like larger state here and smaller state there. And this is due to the hybrid nature of the system. It's nothing to do with discontinuities or something, just the fact that there are certain events which make it happen. Okay, I continue with some basics of nonlinear dynamics. What we have seen is that all of these different types of evolution can be described by ordinary differential equations, stochastic processes, maps, and so on. And the unifying framework is given by flows. So given the state space and the time domain, the flow is just the solution of the system, the time evolution, as a function of initial condition. So phi t of x0 means the state in my state space after time t if I started at time 0, if I started at x0. Okay, that's like something like that. Sorry. So it just tells you where it goes, and it's very useful, this flow picture, because it helps you unifying how you view the system. So if you have this flow, it doesn't matter whether it's discrete in time or continuous. It doesn't matter whether it's stochastic or not. Of course, if it's stochastic, your phi is a stochastic function, but still it's the same kind of setting. And an important feature is the semigroup property. So if you just go from here to there, from 0 to s, and then from s and add time t, it's the same as no, if you first do this and then do that, it's the same as adding up the 2 times and going both time pieces in one step. So x of t plus s is just, well, here it's just because you can add them up, but it's a semigroup property for the flow itself, for the flow function. Are you all bored or are you all over excited? Have you heard all of that before? Can you maybe give some feedback of what your knowledge level is?
I think I unmuted myself. So half of the students, I think they're exposed to these, people from nonlinear dynamics, some computer scientists as their first time. Some of our physics crowd is also their first time. So
thank you very much. So it's good to have everyone on the same footing. The flow is also, I briefly will use it later, but it's, in any case, it's a very useful property if you want to generalize your understanding of the systems. I have a picture here, look. So flows, roughly speaking, transport states in state space with time. And this is a concatenation of 2 flows. You start with your initial condition, you go to phi t of the initial condition, and then you iterate phi s, like another time s from here to there, starting with your new initial condition with x of t. And this is the same as going from here to there in one step. This is just say, this is what this is saying. And for simple discrete time maps, the flow is just a t times iterated map. So phi t of x0 is just g applied to g, applied to g, applied to x0, t times. And for an ordinary differential equation, that's the solution. So for example, if I have x dot equals f of x, you get a solution xt, which is then phi t of x0, where x0 is your initial condition. Invariance and stability. So there are a few concepts of how systems behave. I think the most fundamental one is an invariant set. It's something where if you have your state of the system in that set, you can't get out. And you will stay there because you can't get out, but your time is going on. You stay there forever. So if x in A in an invariant set, then for all times, the flow of starting with x will stay in A. Okay? Very simple. A very, very basic example is a fixed point. You start somewhere and you stay at that point forever. But there could be more complicated examples. For example, invariant sets which have chaotic dynamics. So you have a chaotic a set of points on which the system evolves. So it's not at one point, but at many points. On it, it's chaotic, which I haven't told you what it is, but you have some intuition about. And it stays there forever. It doesn't go away. So an invariant set. Yeah, fixed points, periodic orbits, obviously, chaotic sets, and other things. In a linear system, there are essentially 2 kinds of fixed points, either unstable ones here, like if this is f of x, then if x is large, and here is always 0, okay? If x is larger than 0, then f, the rate of change of x, is also positive. So here it's positive, and here it's positive. In other words, that meaning that here you move into the right-hand side direction, whereas so your state space here is one dimensional. This is the state space, okay? State space. If you are left of your fixed point, you move away in the other direction. In other words, it's unstable. And here it's stable because on the left-hand side, you are positive, you move in this direction. On the left-hand side, you're negative. On the right-hand side, you're negative, you move in that direction. So you go back and it's stable. And this generally translates into whether the derivative of f local to that point is positive, then it's unstable, whereas if it's negative, then it's stable. For a general dynamical system, I'll come to that. It will translate into eigenvalues of the local operator having negative real part to be stable. And if not, then not. Then you can have nonlinear systems. For example, x dot equal x squared plus a constant. And then typically you can have several fixed points. Linear systems don't have stable fixed point, except the trivial one, x dot equals 0, fixed point everywhere. But generically, it has one fixed point and it's either stable or unstable. This one has two fixed points, and in principle, you can, of course, imagine that there are other functions which have like many, many fixed points. And they alternate in being stable and unstable. So two fixed points for this system, one stable, one unstable. Then there's a critical value, which is called bifurcation point here at I equals 0. And well, it's half stable in the sense that the official word is neutrally stable. Neutrally. Which then means you have to look at higher orders. It doesn't suffice to look at the derivatives only here, because the derivative is exactly 0. And third is this case where I is positive and you have no fixed point. What happens is that you very rapidly, you come from the left here, then you slow down because the rate of change is going down, slower, slower, slower. And you increase in velocity again. And interestingly, for this system, the entire path from minus infinity to plus infinity takes you finite time. So, of course, what does it mean? So say you start at x equals minus 10 to the 100, and you ask, when will my system be at 10 to the at minus 10 to the 100, you start, and you ask when the system will be at plus 10 to the 100, which is essentially infinity. How long will it take? And it will take like a few seconds, okay? It will take a finite time. It will not take forever. It will also not take zillions of years, because in finite time, which is small, and you can, for this system, you can actually compute it. You go from here to there. It's interesting to, if you are interested in learning about nonlinear dynamics, this is a very good example. Try to program it up. Make a simple, whatever, Euler scheme to discretize the derivative in time, make the time step very small and iterate, and try to see it. Or if you like mathematics, try to solve that problem. It's a separable problem, so you can solve that by trying to solve this one. Something like that, yeah. You try to solve that, to solve the integral, then you get you have to solve for x of t after you solve the integral. And then you have an expression of how x looks like, and you can plot x of t. And essentially it looks like this. So now this is time and this is x. And well, depending on where your offset is, but if you start at 0 at time 0, like if you started here, you have some time t until which you have reached infinity. So there's an asymptote in this function. I think it's a hyperbolic tangent here. Okay, from these kind of pictures, we can draw what is called a bifurcation diagram. And in the simplest case, it draws the fixed point, which are these guys. As a function of parameter. So here's a parameter, there's a fixed point, and there, if it's stable, you draw it as a solid line, if it's unstable, you draw it as a dashed line, and you see that here the bifurcation diagram is relatively simple to understand. For positive I, there's no fixed point. For negative I, there are two fixed points. The negative one is stable, the positive one is unstable. And it turns out that this guy is a parabola as well. And by the bifurcation diagrams, you can distinguish different types of bifurcation. So once you see something like that, this is called a, this bifurcation is called a saddle node bifurcation. Saddle node bifurcation. And every time you see something like this, in any of analysis of a complex system, you can also do that numerically. You can be reminded of a saddle node bifurcation and say, like, oh, maybe something like that is happening. Maybe some part of some function is going through zero somewhere. So I understand things. And you can also understand the scaling. So if it's a parabola, this means it's a slope here is infinite and so on. And you can compute the scaling, which is like a square root scaling. And the square root scaling you can in turn extract from data, either real data or simulated data, even without knowing the model. So it's a very interesting and important because you don't need to understand the model to understand the bifurcation. Bifurcation is something qualitative, a qualitative change in a qualitative model. Okay, very quickly about high-dimensional systems. You have now a high-dimensional system like an n-dimensional system, and we focus on differential equations. You take a fixed point, which is also an n-dimensional, where f of x is an n-dimensional zero vector. You have a local Jacobian at your fixed point, and the Jacobian is just, it's written like this, but it's just a matrix of partial derivatives, df1, dx1, dfn, dx1, so on. And the eigenvalues of A tell you about stability. The fixed point is stable. Fixed point is stable if all eigenvalues have negative real part. And it's unstable if some eigenvalues, for example, only one, has a positive real part. If both is not true, for example, if one eigenvalue is exactly zero or has zero real part, and all the others are negative in real part, then what? And this is also a common problem, like if you have systems with symmetry or tuned systems so that one eigenvalue is exactly zero, and there's none of these cases, you have to again go to higher order. And the interpretation is that if it's stable, there's no direction along which perturbations, like going away into that direction from the fixed point. You start at fixed point, you go into some direction, which might be your eigendirection. And if you go away, you decay in that direction because the eigenvalue in that direction is negative, then this means you get a dynamics proportional to e to the minus, no, actually plus e to the lambda it, which is proportional to, which is equal to e to the real times e to the I imaginary part it. So this one just cycles. This one is this in the complex plane, and this one, if the real part is negative, decays. So this is e to the minus whatever beta t times something which is oscillating. So if that's true, you would go back to the fixed point. And if that's true along all directions, you always go back in one way or the other. So if there's an imaginary part, you may oscillate around it. If z is 0, you don't oscillate, just decay to it. Same for maps. I think I skipped that. It's the same story, except that now eigenvalues need to be absolute value smaller than 1, because you want to contract state space. Yeah, I think I don't go into detail because we don't need that. Networks. Networks are everywhere and most are dynamic. And networks are essentially a collection of nodes, which are I typically say units if I talk about the dynamical system. Sometimes you want to say variables, but that's not always the same, because a single unit, for example, a nerve cell, might have several variables you want to describe it with, or not, depending on what you want. Elements of vertices interacting via links with other nodes. And the links are also called edges or connections. And I think all of you have seen that in one or the other circumstance already, maybe also in this lecture series. Now you pick your favorite system, for example, your social network, your neural circuit, your gene regulatory network, the traffic network around you, communication network, anything. Pick your favorite one, okay? Do you have one? Pick one. Not necessarily from the list. You can just make up whatever you want. And now assume next week it will not work. Okay, for 1 week, your selected network will not operate as you desire. Then most of you, if you have picked any reasonable network, will be in serious trouble. Like even if you picked only the social networks, that's maybe one of the least hard ones, then you don't have any social interaction next week, which is a bit weird. I don't know many people who do that. If your neural circuits don't work, you can't listen to my talk, which would be very bad. If your gene regulation doesn't work, you will be dead within a week. If traffic networks don't work, you can't go anywhere. If communications networks don't work, you can't communicate with colleagues, friends, and the internet. And if power grids don't work, you don't have electricity. Again, same problem, you can't listen to my talk.
Well, that's kind of the norm here. We're running on a power grid, which pretty much is shut down.
I'm happy that so let me know if I should.
We have redundancies. We've developed them over the years. So
write an email to Elon Musk whether he wants to send some battery storage. Okay, yeah. So all of these systems abound and they are critical. Really, I mean most of them. Then there's this network aspect, and first there's the dimensionality aspect. As I've shown you just before, one-dimensional linear systems can only have one fixed point, whereas two-dimensional ones can have things like periodic orbits, and three-dimensional ones can already have chaos, like very complicated dynamics. And in higher dimensions, like here, this section of a grid, you can have things like waves and patterns and so on. And then there's mathematicians and physicists and all kinds of modelers who go to investigate the continuum limit, like infinitely many variables. And already in his 1994 book, Steve Strogatz, from who I learned during my research scholar time at Cornell University, he published in his book this nice table about where the frontier of research is. This is this line, and it's a one axis here is the number of variables from 1 to many to, well, moderately many and many to infinitely many, and nonlinearity. Of course, it's not quantitative here, but these are linear systems, where these are nonlinear systems. Today, most of these, like almost 30 years past, most of these subjects have moved down. They are now considering nonlinearities everywhere in civil engineering, in electrical engineering, solid state physics, molecular dynamics. Everything is now taking into account nonlinearities because they are important. But the main point here was that there's this frontier, which is like many variables and and nonlinearities. And these at the time have been like unsolved problems, and most of these are still unsolved. There has been progress in also most of them, but they're essential problems which hinge on the fact that there are nonlinearities and many variables. So in other words, it's really complex systems. I would like now to take an argument and say, look, there's another axis which is essential. And this is the interaction topology, like how the many variables interact. Of course, for one is stupid and for two is simple. But once you start with three, it becomes interesting. And the interaction topology is something which tells you, well, it tells you who is interacting with whom and how. And these lines here now represent some different types of interactions. They could be directed or not, like directed interaction. And this is undirected. Unfortunately, the vocabulary is like that undirected is the same as bidirection. So two directions or no, it's the same. Meaning that they are mutually influencing each other. And for linear systems, most of it is known, like there are still some theoretical progress going on in optimization and so on, but most of it is actually known. For example, Kirchhoff's laws, well, there are two. Random walks on linear systems and so on. There's already for networks, there's no continuum limit. Like if you, in contrast to grids, like here you can imagine you have a continuum limit. If you make this thing larger and larger at some point, and you shrink the entire thing, like you make more nodes and shrink it to the same, you can imagine you have a continuum which has some type of local interaction, but you can characterize it efficiently. Here you can't, there's no continuum limit, and for nonlinear networked systems with many variables, there's essentially nothing. Of course, there are lots of examples, like I know there are probably 10,000 papers on that, but there's very little on any broad fundamental theory which is like applicable, like in nonlinear dynamics. Okay, stability of fixed point, here it is. Or wave theory for all kinds of continuous space models. There's nothing like that which is fundamental, applicable to most of networks, say. If you know anything, let me know. I'm happy to discuss it. Yeah, and network topology, of course, coacts with the nonlinearities. And I mentioned already the speed limits, and we also have a nice paper on with Christoph Kiers on remote action. You change some, so imagine you have three brain areas, A, B, and C. And you are asking for the communication pattern between A and C, the information transfer between A and C. Okay. Maybe I should draw that. With one subnetwork, there's some interaction here, another one, and another one. You are asking what is information. No, this is not good. You are asking what kind of information is transferred from A to C per time or whatever. For example, in your brain network, or you can imagine any other network. Now you make a local change here. Yeah, you change some parameter change. In B. Could you imagine, where's my, doesn't work, oh, here. Could you imagine, so say originally the information flow is from A to C, net. There's more information flowing from A to C than the other way around. Now you make some change here, and afterwards, oh no. Afterwards, you are reversing the information flow direction. This is in this paper. Okay, that's just one of the collective aspects in that paper. It's very interesting. Well, not necessarily about the details of the paper, but really of the conceptual consequences. You change something in your, say you change something in your auditory cortex. This is like your sensory cortex where signals come in. This is auditory. This is in a mouse or something. This is motor cortex, like where you initiate movements. You change something in your auditory system, and then your information to the motor system from the sensor system is changed. How is that possible? Like no one would believe us initially, and well, it's just a property that you have a state space, and well, state space is state space. So every variable can, in principle, influence each other, in particular collectively. You can indirectly influence. And I think I don't go into details here. All kinds of networks have different types of links. For neural circuits, it means that neurons send signals, and which again is a discrete thing. Okay, similar to computer networks or communication networks. Schwupp. And now I show you one more example, and then I end for today. I discuss a very interesting phenomenon in a model which is called Kuramoto model. It is a model of weakly coupled oscillators. And the oscillators have only one variable, which is a phase. So all state space is on a ring. Yeah, something like that. On a circle. Okay. This is the phase here, phi I. And so the full state, the vector of all phases is just in 0 to 2 pi to the n. Okay, there are n of these guys. And there's this okay, the rate of change of each is given by an intrinsic frequency. So they just run around the circle. And then there's coupling. The coupling tells you that all those j, which are in the input set of I, this is node I. There are certain guys, J1, J2, J3, and these are all in my input set of I. And there are other nodes, like here. There are other nodes like J4, which is not in the input set of I. Okay, it's not connected here, there's nothing. So this is what this means, is you sum over all inputs, and then there's a sinusoidal coupling with the phase difference. So the closer you are, the weaker the forces, right? Because the sine function near 0 becomes 0. And now we take an ensemble, which is a collection of possible network topologies, and we take those for example, with 100 units each, like 100 variables each, and 5% of the edges present. Like each guy on average has 5 inputs. So what you do is you go to every possible edge in the network, every pair of nodes, and you toss a coin, or you draw a random number. If the random number is smaller than 5%, 0.05, you put a link, a directed link. If you don't, directed. If you don't, there's no link. Okay, this is what you do. And we make the coupling attractive. Attractive meaning that you want to synchronize, you want to put the phases tend to become similar. And now you draw one realization, and what you see is that all phases have become similar in the long run. And the average phase deviation looks like that. Delta phi is just the average compared to the deviation of each phase phi I compared to the average. And well, a very simple synchronous state. All of the 100 units have the same phase, relative phase to 0. And of course, they're all running around. I didn't say that I take very simple assumptions here as well. So all the frequencies are the same, like very basic stuff. Now you take the same kind of network parameters, but a different realization. You just draw a second network. You take everything the same omega, the same j's, everything the same, except the topology is different. It's a different realization, but from the same statistics, okay? And what you get is this. And when I was first seeing it, I was saying, okay, maybe there's something wrong. Maybe there's numerical outliers here and it didn't converge or whatever. And on second stage, I thought that maybe there's something interesting instead of wrong. So again, attractive interactions, all are the same. These are the same. And this is implying like you can mathematically compute it. You can compute the stability of the in-phase synchronization state, which is the fixed point in the co-rotating frame. You take a reference frame of reference which rotate with all the oscillators, then it doesn't rotate anymore, then it's a fixed point. You can compute the stability of the fixed point, find that all the eigenvalues except one are negative real part, and this means that the solution is asymptotically stable. And it's independent of details of the topology, of the exact parameters and so on. Okay? And random initial conditions sufficiently close to the synchronous state end up in synchrony here. Okay? Here means in this realization. And I've shown it's stable, right? There's all conditions satisfied that it's stable. There's no guy with a positive real part eigenvalue. Under no circumstances, no parameters, no network. But there are eigenvalues with 0 real part. So how does the heterogeneity emerge? First, we need the concept of strongly connected networks. So this is a strongly connected network because from each node, you can go to each other, to every other node. For example, from here to there, you can go by following this path. But you can also go from here to here by following this path. So, and there's a network is strongly connected or just connected if there's a directed path between any pair of units. Okay? Strong connectivity. It's important for just general knowledge that strongly connected does not mean that the coupling strength is large. Okay, could be weakly coupled, strongly connected is possible. Now, of course, there's the other opposite extreme, which is disconnected networks. You have if this is one system, you have like cut it here. And then you have two independent systems. It's not surprising that they, for example, would not synchronize, right? Because they don't know anything about each other's states, so they cannot cooperatively act. Then there's a notion of weakly connected networks, which is a notion in graph theory for directed graphs, where you can go for each pair of units, there's a path from one to the other, but not necessarily vice versa. For example, you can go from this guy to that guy by following this path. But you cannot go the other way because here you stay there, right? You can't go here this way. There's nothing which brings you back. And that's why we call this guy, this is a strongly connected component. Strongly connected component. Oops. We call this strongly connected component a source because you can go out but not back in. Yeah, strongly connected components are strongly connected subnetworks, which in itself strongly connected. Between them are only unidirectional connections. So there could be more connections in this direction from STC1 to STC2, but there cannot be any connection back. And now let's consider a toy example of what we have just seen in the synchronization phenomenon, something which is heterogeneous. So here you see this random, this network with 11 nodes. The red is a new link coming later. And so we have a black network, and this is the final irregular dynamics pattern. So this is our model of the model. We simplify the problem until we find a good model, and this turned out to be a good but non-trivial one. And the phase ordering, we now order these guys by phase. We group phase. You see here that these three are the same somehow, and then you find out that these are also the same, and the others are not. And so we group them like this. Takes this group, that group, and the third group, which you don't resolve yet. And you just re-index the guys and plot it again. So the decomposition into strongly connected components is somehow important, right? Because this one, 7, 1, and 6 are one strongly connected component, and 8, 4, and 2, and you can't see it here, this is number 2, are another strongly connected component. And well, here's another one, and here's another one. And so this is the substructure in terms of strongly connected components. And now think about this red line. So you make a line between 8 and 6, which here seem to have nothing to do with the other, 8 and 6. You make that, you add the line, what you get is a homogeneous state. Immediately, like this is a final, not immediately, like after a transient, this is the final state. You have, and the interesting thing here is this is true for arbitrarily large networks. You can have 1 million nodes with 10 million links. Everything is heterogeneous. You add one link and you get full synchrony in the entire network as the final attractor, like the final state. How do the strongly connected components control the dynamics? So there are 4, and with one link, you can't make it less than 4. Actually, the strongly connected components are still the same. There's still these 4 guys. Yeah, so why does this one link make a difference at all? It looks like super strange because here it was heterogeneous. Only after we ordered it became somehow homogeneous. And here it's completely homogeneous, although we added only something at some randomly looking nodes. If you do the stability analysis, you find that close to the fixed point, close to the point where you're operating, the phases in one along one cycle are actually averaged. So the new phase after one cycle, this is now a map, is approximately, meaning in first order, is approximately given by a matrix times the phases originally, and the matrix has a weighting. It acts as weights. So weights sum up to 1, and they are between 0 and 1. Okay, so the total is somehow a weighted average over the phases of the input feeding unit. In other words, including itself. Okay. In other words, if you have, do I have a picture? No. If I have a unit I here, you have your 3 nodes. Then there are different weighting factors, J1, AI, J2, AI, J3, and this is local, like more or less local feedback is AII. And this is the sum, the phase of this guy after one period or one time characteristic time scale is the weighted average of every guy here, including itself. Okay, this is what this is saying. Now, now we're talking about strongly connected components. So these are strongly connected components. 1, 2, 3. Okay, there can be some substructure among nodes, but we know that if it's strongly connected, then the average is actually balancing out. Like if you have a strongly connected network, we observe that everything is going to synchrony. And you can also prove that. Now, if that one is going to synchrony with a relative phase phi a, and this one is fed averaging over each neighbor, but also over this, whatever comes in here, but over this phase phi a, that after a long time, if you always feed the same number and averages over this number and whatever you had before, you will at the end have only that number left. So this one will also converge to phi a. And same here. So you have a fully synchronous state because the strongly connected component structure, the meta structure of your network, meta structure or topology on the level of strongly connected components is like that. It averages states here and whatever is here, but it does it repeatedly. And at some point, it lost all the information here because everything is more and more adapted to phi a. Now you have the same thing with with one additional strongly connected component. This goes to phi A, but this one doesn't communicate with the other one. Okay, so this one, let's call it 4. The strongly connected component number 4 has no information about what the state of strongly connected component 1 is. So this one would just go to also one phase, but to another one, which is I call phi B. And then both phi B and phi A influence the second one. And so this will go to some value in between. Actually, this is only in quotation mark, because it might actually depend on the node. Depending on node, I in SCC2. Yeah, so this one might be heterogeneous. They might all converge to different phases depending on the exact structure of what's going on here. So it depends on the structure here and where the inputs are. These are only symbolic, right? It could mean that there are several individual links here going like that to different nodes into the network. I shouldn't draw that too much because it's complicated. So these are links between components, and they represent many possible links between individual nodes in these components. And so if this is heterogeneous, then this one, well, is also heterogeneous. It goes to something, but it's either, if it's homogeneous here, that would go to the same one, but if it's not, well, depending on what the topology here is of the connections and the topology in that third strongly connected component. And now you can understand what's going on. If you have 2 or more sources, you will be heterogeneous. If you have one source, everything will be fed from that source. This is always giving the same signal, like exactly as it was here. You have one source, and here are 2 sources. So one source, and you change the property of the entire network of having one source strongly connected point or several, but actually 2 to 1, by adding only one link, which is this one. Okay, this is the new link. And you see that it changes the overall structure from this pattern to that one, where there's only one source, whereas here are 2. So this one is heterogeneous, this one is homogeneous in dynamics. And because we have the math behind it, I don't go into details there, but because we have a linear approximation to the weightings, you can actually compute or estimate how the heterogeneity is influenced, depending on all the details, depending on the substructure of who is influencing whom, how these guys look like, and so on. And of course, you can imagine you have larger networks, and it always works. Like this is a prediction now for our simple network, linearized. The dots are the real data. The crosses are our linear prediction of where the heterogeneity how would it control how would the topology control the heterogeneous dynamics. With that, I'm close to 2 hours. Half of you will be asleep and half of you will be absent already. No. So take-home message: a network strongly connected component substructure alters the dynamics. Like depending on whether you have one source or several, it makes a big difference. And you can change the number of sources by putting individual microscopic links, like links between individual nodes. Disordered dynamics for more than one source. And mind that you can globally change the substructure by very few actions. So say you have strongly connected components 1, 2, and so on. And they're connected like that, right? Now you would think, oh, that's very bad. Maybe like this even. Oops. So here it's simple, it's one source. This is the source, right? And if you remove this one link, you have two. And for each link you add, you can remove one source. So here you can remove one of them. And from here, for example, you can put that link and then you have one source again, which is now this one. And it changes everything globally downhill. Okay, it can be arbitrarily long chain here and changes the dynamics here if you change something there. That's the same kind of phenomenon I reported about the information flow direction. You'd make a local change somewhere in your system and can have drastic influences in the entire system. And on the conceptual, so this order dynamics is characteristic of the topology on the coarse scale. How do the strongly connected components compose the network? And today's on a more overarching perspective, we have taken a forward perspective. So you have, I've told you, you have a network with this dynamics, it has that, no, sorry, with this topology, it has this dynamics. And if you change something in topology, it has that other type of dynamics, disordered or synchronous. Tomorrow, starting tomorrow, we will take the reverse perspective or inverse perspective. We'll try to solve some inverse problems. Can dynamical measurements reveal aspects of the system, like from dynamics to topology? And this will be covering the next two lectures. One is tomorrow, and the other one I forgot, 20th.
I guess maybe? It's the 14th.
14th, okay, next week. That's good. And I'll look forward to first of all give the other talks, but also for now have questions from you and comments. And also, please, as I said, please email me, please tweet me if you want, or ask, even better, ask questions now or during any of the other sessions. Thank you for your attention.
Thank you so much. I personally want to thank you for the walkthrough from the basics, like from the very, very basics of nonlinear dynamics and stability, all the way to introductory notions of network topology and strongly connected components. So it was a very good walkthrough. I guess the crowds from nonlinear dynamics were happy with, they were nodding their heads. They knew the stuff. The other students were kind of learning as the lecture was going. I'll leave them for some questions if any of them have. Yes, there's a question in the back. Just press it. Okay, then you can use mine.
Hello, thank you for your lecture. It was amazing. I have a question at the beginning of your lecture when you were talking about the request and the drivers and how they are matched. I want to ask a small question. Is there some criteria they are matched on, let's say an optimization problem, or is there a mathematical equation where the algorithm matches both the requester and the taxi? Sorry.
Yeah, very good question. So first of all, on the general side, maybe I have to say, on the one hand, this was an introduction, but on the other hand, it's not, of course, a comprehensive introduction. I picked some of the aspects which I might want to use in the future, and also I try to give you somewhat of an overview of our motivation of what we do besides inverse problems. And the topology problem I just explained was to motivate you that, oh, there's some information in the topology which expresses itself in the dynamics. And this means, of course, that if you can figure out what it is, you have information about the topology if you know the dynamics. Let's go back to the taxi. So you were asking whether there's any algorithm or a match dispatcher, right? And so the dispatcher here is very simple. It first asks who was requesting a taxi first, and whoever that was gets the next taxi. And the second request, and you can imagine in a real situation, for example, I've been living in Göttingen, Lower Saxony, Germany, for almost a decade. And they have a taxi service which exactly works like that. So the request is broadcasted, and the taxi drivers who are free are available of taking that next request. And so it's first whether they are free, and second, of course, nearby taxi drivers would preferentially take the request. So this is the algorithm here we have implemented in. It's not really an algorithm, just the first come, first serve service. And in some sense, it's arguably fair, because if you ask early, you get the next available. But it's also arguably inefficient because what I explained, that it makes the system inefficient. Now you can think of more advanced dispatchers, and I've shown you a less advanced one, which is the mixture of both, right? This one. It's the mixture of two dispatchers. One you apply to randomly to whatever 40% of the taxis or requests, you apply that, and 60% you apply the other one, which is now a nearest first algorithm. So you collect over. So one way to do that is to collect requests over a minute or something, or 2 minutes, until you have many requests which are then again distributed across Manhattan in this case. And then you take out of the, say you have 200 requests and you of the order of 200 taxis, then you take the nearest taxi given it is in this 1 or 2 minute interval. So it's a slight difference only, but for the person who requests, if I told the customer, sorry, I will not serve you now, and maybe I will take 10 other people before your taxi is even sent onto its way, it might be assumed as unfair. So yes, you can. There are certainly ways of optimizing that, but the real problem the real conceptual problem is, given any real system, typically real taxi operators or ride-sharing operators, they have existing algorithms which are somehow optimized for all kinds of things. And they are very complex. And depending on what, they might not get hysteresis, but they might get other factors. So once you start with the optimization process without thinking about the collective dynamics first, you typically run into collective challenges, say, not always problems, but challenges. You run into dynamics which you have not foreseen. We have also a 2020 paper about Uber drivers and the supply versus demand congestion. So what people have found in the news, like journalists actually have reported in the newspapers, is that drivers collectively gather on parking lots near the airport or on the airport, and they coordinate to all switch their apps off, like being not available, okay? And then what they did, they exploited Uber's internal algorithm, which was setting a price depending on supply-demand balance. So if you have reduced supply of drivers, then your price would go up. So at some point, they coordinated that they all switched the app on again, and then they could serve the same customers at a higher price. And that's a coordination. So it's also some effect of how an optimized algorithm, which is supposed to do the opposite, like supposed to balance it more, actually balanced it less because there were reactions to it. So that's a typical complex systems problem. I'm just saying now, you can remove hysteresis here if you have a clever algorithm, and you can also have it as fair as you can with a dedicated optimization algorithm. But typically in a real system, you have so many dimensions that you then get another challenge, which is always of collective nature.
Thank you.
What you wanted to hear? I don't, probably more than you want to hear.
Yes, sure. Thumbs raised, so she's far in the back. Another question, which if I understood it correctly, I've received it. In the strongly connected component, in the last thing you showed on synchrony, is there an underlying assumption for strongly connected component to appear when there's a steady state behavior? So can this inference about the topology or the knowledge about strongly connected component be inferred without the system exhibiting a steady state?
That's a very good question, and I think let's put it like this. So you're asking whether, so all of what I've shown you is steady state, right? You are asking whether I can reveal the structure of strongly connected components from non-steady states if I have the dynamics.
Yeah, absolutely. So there's no, I mean, here you kind of waited until the steady state is reached, and then you could group them into a strongly connected component. Can one infer something about the dynamics without the need for a steady state?
It's a very good question. In general, you cannot, because you can always make up examples where just the information is not flowing your way. So, so tomorrow I give you an example where you get the entire structure out, but the information is, the condition is that the entire thing is strongly connected. So what you cannot get out in general is the substructure of any strongly connected component. For example, this one, okay? Where you see three, this was wrong. Let's take this one. 7, 1, and 6, okay? These guys, by construction on the invariant set, so after the transient, you cannot distinguish these. So there's no way you can in any way distinguish whether, for example, this link is coming from 7 or from 6 or from 1, right? It's just not possible because the information is not there. If you have a dynamic picture, you could imagine getting that out. The honest full answer is I don't know, but also it's a good question, right? It's probably an open research question if you want to discuss it. Like if you take the transient into account, can you what aspect can you reconstruct from the topology?
In what sense can one like approximate systems linearly around, like, let's say, very short time frames, then recover a time-dependent network?
A time-dependent network?
Yeah, so it's like it's assume that you start fitting the data or the evolution of the trajectories over consecutive intervals of time, and you, let's say, approximate x of I as a linear combination of some neighbors. Mm-hmm. And that's going to tell you how this particular node is connected to these at that particular instant of time. And then you do it iteratively over so many intervals, and thus recover temporally evolving networks.
So essentially, temporally evolving networks, you mean that links appear and disappear?
Exactly, in the sense that, you know,
Okay, so
resultant
what you're asking is essentially a sequence of networks. Your answer would be at this time interval we have this network, and the next time interval we have another network, right?
Yeah.
Yeah, one can think about that, and of course, if there's timescale separation, like if the changes are small, then you can essentially locally determine when things change, and you can also detect when they change. So you can say what the structure is at one interval, and you can detect when the structure changes. It's more difficult if your changes are fast. Like if the changes are happening on the same time scales as your dynamics, your intrinsic dynamics, then it's harder. And I wouldn't know how, because you have just too little information. You can probably approximate something, like in the sense that give some coarse scale information, possibly about the strongly connected components or something like that. But I doubt that you would get out the full network topology. It will be, I think, more apparent tomorrow after the talk when I explain how in a strongly connected setting, everything is strongly connected, you get out the entire network. It's also related to observability, where I'm not expert, but it's closely related to that. Because so essentially you somehow need to have the availability of information, say, in your measurement. If you don't have that, then you're lost. And there are two aspects of availability. First of all, whether you have any kind of influence of what you're looking for in your dynamics, and the second is whether it's sufficiently much. Like if you have, for example, in one part of the talk tomorrow, we need linearly independent measurements, and well, if they are not numerically sufficiently independent, then it doesn't help.
Yeah. Okay, thanks. I guess if the crowd on Zoom, no one has a question, I think we can call it a day.
There's also a smaller crowd now. Anyone?
We have a question in the crowd.
I don't see any question, but maybe.
I just wanted to ask that when it comes to the stability of our system, is there any manipulation or recommendation to improve its stability and reduce the steady state error?
Which system are you talking about?
The control system.
The control system of what? The robot?
In general, yes.
In general. Oh, yes, but that is hard. I mean, you can always you can tighten the control, right? That makes it more stable with control, but it's not always what you want, because you typically want the system to have flexibility. I mean, the limit of infinitely strong control, you just don't move at all. You just stay at a point. And that's a very boring system. So it depends on the question you have about the system.
Okay.
We currently, I don't know, maybe I should also delay that. Yeah.
All right, I guess we no longer have questions from the crowd. Really want to thank you for your generosity today, like really building up from bottom all the way up. And I think they're going to realize the importance of this first constitutive lecture in the upcoming ones. So thank you very much for your beautiful talk today, and we're looking forward for the upcoming ones.
Yeah, thank you very much, everyone attending, and also for the kind invitation. The next talks will be more advanced and also a bit more superficial, in the sense that I can't go into all of the details. But I try to convey the messages and refer you to literature, and also explain the mechanisms of why things work. And yeah, so I hope to be able to cover a bit more ground on the inverse problems. And I hope you've gotten an idea of why the influence of a topology onto the dynamics can be like inverted, and trying to get out information about the system from the dynamics.
I
Thank you
think
very much.
I'll convince them by giving them a homework to work out the ODE for the Kuramoto for tomorrow.
Oh, okay. Lots of work. Yeah. And you are already behind my time, so it's what, 5:15 at your place, right?
Yes. All right.
Okay.
Thank you so much.
Have a successful afternoon.
Thank you.
Thank you. See you tomorrow.
Bye.
Bye-bye.